I get bored sometimes. I'm sure astronauts get bored sometimes.
Yeah, I'm pretty bored.
Yeah, me too.
And when we're all starting our 6-month journey from Earth to Mars, we will all probably get bored at some point. What's a better cure for boredom than turning the kettle on, making a cuppa, and switching on the telly? How our TVs will be powered in space. Space travel presents a lot of weird problems when it comes to storing and collecting electrical power. Electrical power is needed to operate and support pretty much all equipment, from computing and communications to sensing electronics and entertainments for the travellers. It can be used for propulsion in the form of ion drives or for separating water into the necessary elements needed to make fuel. I'll go over some possible power sources for space travel, from the use of batteries to miniature nuclear power plants. Solar power. Most of the satellites we have in Earth orbit right now are powered by solar arrays. These contraptions consume quite a lot of space when in action, but are easily folded up at launch and deployed once in orbit. We've seen a great development in photovoltaic energy in the past years, including efficiency of light to power transformation, but the intensity of sunlight at the distances we need means that we still need quite a hefty mass of solar arrays to power anything useful. More mass on the arrays means less mass used for other payloads, and more powerful rockets or maneuvering systems are needed for our rockets. This adds up to quite the cost. For operations such as outer solar system travel, these maneuvering systems wouldn't be as important, but there are far greater benefits to using other power sources, such as RTGs. One concern had about using solar panels on the Mars rovers Spirit and Opportunity was that the main sources of power, solar panels, would be covered up by dust, leaving them useless. Thankfully, the wind on Mars turned out to periodically clear dust off the panels, which was pretty cool. Nuclear power. The probes we send out a long distance from the Sun use its radioisotope thermoelectric generators, RTGs. These devices contain small samples of radioactive materials, often plutonium, which produce heat from radioactive decay. Thermocouples convert some of this heat into electric power. The radiation from the fuel is not used by the RTGs, but there are designs that produce electricity from captured beta particles. Why is an RTG better than a solar panel? An RTG works in any environment for a long time. The Voyager probes, the most distant artificial objects launched by man, are both powered by RTGs and are still mostly functional. There are no moving parts in an RTG, and fundamentally they're very simple. They consist of a fuel cell, thermocouples, and radioactive shielding. Compared to the earlier Spirit and Opportunity rovers, Curiosity uses an RTG to produce electrical power in order to charge a lithium-ion battery pack. It can operate at night, in dust storms, and it's able to use large amounts of power at day and then recharge at night. However, RTGs are very inefficient. Curiosity's RTG produces 200 watts of thermal power, but only 120 watts of electrical power. This amount of heat waste adds engineering challenges that other power sources don't face. Even when electrical power is not being used or produced, thermal power is still produced at full capacity, which has to be dumped. In addition to this, great effort must be made to keep the RTG at an acceptable temperature while on Earth. Safety considerations must also be made due to the presence of radioactive material in order to not irradiate the people around it. Fuel cells. A semi-temporary solution, fuel cells were used for both the Apollo and Space Shuttle missions. Fuel cells combine two chemical components at a controlled rate to produce heat, electricity, and some chemical waste. In the case of the best contender, hydrogen-oxygen fuel cells, the waste product is water, which is highly useful for the crew. Fuel cells require a lot of support equipment, bringing us back to the problem that the solar arrays face of adding significant weight. More equipment also means more chances for failure. The two fuels must be stored in cryogenic tanks for hydrogen and oxygen. The fuel transport pipes can also fail mechanically. In fact, the famous failure of Apollo 13 was caused by an exploding oxygen tank supplying fuel cells and air to the crew. This point of failure meant that the electrical power on the spacecraft was heavily limited, and endangered the crew who had a far more limited supply of breathable oxygen. Batteries. Non-rechargeable batteries are not exactly viable on most spacecraft as the main power source, although small amateur satellites do use them for short missions. Power sources for human exploration in space have to be long-lasting or somewhat renewable, and in most cases, batteries don't fit this. Rechargeable batteries have been used to provide continuous power for satellites that move in and out of sunlight, and one is used in tandem with the Curiosity RTG to power large electrical loads, while the RTG is used to provide a lower but constant amount of power. The future brings many new discoveries. We are still finding more ways to make our solar panels efficient. NASA is investigating producing small amounts of plutonium-238 for missions in the event that Earth runs out of fuel sources, and the use of wasted heat energy in radioisotopic Stirling engines is being considered. Right now it looks like RTGs are the most probable source of power for the majority of human space travels. So look forward to the future, where you'll be lounging in your cabins, watching TV shows, and listening to music powered by your own miniature nuclear power plant.